Hi there guys, welcome back to my chemistry YouTube channel. This video will be on electronegativity. I picked this topic because I think especially for chemistry A level, this is the most important thing that, definitely one of the most important things that you need to know about. The reason for this is because it comes up in so many different areas of chemistry. For example, reaction mechanisms, predicting how molecules will interact with one another, and then it also comes up when we're looking at acids and bases and determining which acid is stronger or which base is stronger and all stuff like that. So let's actually just first of all look at what it is. So you may have heard of it before, you may not have. Electronegativity is basically, it's the ability of an atom to attract a shared pair of electrons in a covalent bond. Okay, so let's type that out. So the in white would be good, wouldn't it? The ability of an atom electrons in a covalent bond. Okay, so that is our very kind of basic definition. I'll explore this idea further now. Oh my god. Right, there we go, it's back. Okay, so what does this actually mean? So if we look at a hydrogen molecule, okay, this is arguably the most basic molecule ever. It contains 2 electrons here and here, and I drew them, you may notice that I drew them exactly in the center of the bond. Okay, now the reason for this is because obviously it's to do with electronegativity. It's because the difference between the electronegativity is 0, and this is, hopefully this is obvious because they're the same molecule, they're the same atom, sorry, which obviously means that the difference will just be 0 because they will have the same electronegativity value. Whereas if we compare this to, let's say, hydrogen and chlorine, okay, the difference between these values is not 0. In fact, chlorine is more electronegative than hydrogen, so the electrons in the bond will be approximately here. Okay, so they'll be a bit shifted over to the right. Okay, now if we compare that to hydrogen fluoride, okay, the electronegativity of fluorine is even greater than hydrogen, and as well as greater than chlorine, which basically means that the electrons will be even further to the right of the bond and much closer to fluorine. Okay, so I'm going to bring up a table now and we're going to explore why that is. Okay, so here's some values. Okay, so we can basically see that fluorine, as I said before, is more electronegative than chlorine, and then therefore hydrogen. So electronegativity, it increases across the group, increases up the group, sorry, and it also increases across the period. Okay, roughly. These atoms, I'm not going to go into why they're a bit different, because you don't need to know it for A-level chemistry. You just need to know that typically electronegativity increases across the group, up the group, and increases across the period. Okay, so why does this actually happen? Well, if we look at a hydrogen molecule, for example, we have 1 electron in its outer shell and 1 proton. Okay, so obviously you may have heard of things like electron shielding and atomic radii and atomic size. So let's just contrast this to fluorine to make it an easier comparison. So if we compare that to fluorine, fluorine has 9 electrons in its outer shell. Sorry, 7 electrons in its outer shell, 9 in total. I'm not going to differentiate between p orbitals and s orbitals yet. I'm just looking at subshells. So, and obviously it has 9 protons. Let's just draw those as dots. Is that 9? 1, 2, 3, 4. There we go, 9. Okay. So basically, what this means is that because fluorine contains way more protons, well, it contains 9 times the number of protons than hydrogen does, the attraction from the center of the atom to the outer electrons is much greater than the attraction of the hydrogen to chlorine. Than the hydrogen protons to the hydrogen electron. Okay. Now, what this means then is that because the attraction is greater, this means that the ionic radius is smaller. And well, you may ask, but what about the shielding? Because obviously hydrogen doesn't have the hydrogen electrons. There's no shielding. So obviously it's a smaller atomic radius. However, because fluorine only contains 2 shells anyway, the shielding experience from the first to the second subshell isn't very much at all, and is essentially nullified when we add 9 positive protons in the nucleus, which attract those electrons and shrink the atomic radius significantly. So now what we can do is we can actually have a look at some electronegativity difference, which is represented by XD. Okay, so if we go down here, we've got electronegativity difference. Okay, now there's an equation for this. The equation is the electronegativity of atom A minus electronegativity of atom B. Okay, so if we look at hydrogen, let's actually look at why is the difference between hydrogen and 0. Well, if we do this, it's 2.1 for hydrogen, as it says here, minus 2.1, which is 0, which means that it's not an electronegative molecule, it's non-polar. You may have heard of that word before. If we then look at the difference between hydrogen and chlorine, so let's look at it's 3 for chlorine minus 2.1 for hydrogen, which equals 0.9. Okay, this means that there's a difference between electronegativity, which means that it's a polar molecule. Okay, if you compare fluorine and hydrogen, we have 4.0 minus 2.1, which equals 1.9, which obviously is an even greater electronegativity difference, which means that the molecule will be even more polar. Okay, but you may be thinking, obviously, look, it's great that I can see that 1.9 is greater than 0 and 0.9 is greater than 0, but what about distinguishing between these two? Okay, so there are actually some rough values that we can take a look at. So this is to do with the covalent and ionic bonding that I mentioned before, how they're the same thing, they're just 2 extremes of the same thing. So if we look at covalent bonding, okay, we know that in covalent bonding, it's 2 atoms share a pair of electrons, whereas in ionic, it's 1 atom will take the electrons from the other atom and become negatively charged, whereas the other becomes positively charged. Okay, so let's look at the reason for this. So what I'll also do quickly is I'll just write non-polar. Non-polar, polar, and ionic. Okay, so I'm gonna create some values which are true. I've not just made these up, and this basically can give you a guide to whether a molecule is polar or non-polar. So if the electronegativity difference, if it's less than approximately 0.4, it means that the molecule is non-polar. So this means that, like, hydrogen is non-polar because it's obviously electronegativity difference of 0. This means that the hydrogen to carbon bonds, that's non-polar, it's 0.4. So all these bonds, they're non-polar. Okay, polar is basically between In fact, let's do ionic first. So ionic is if the electronegativity difference is greater than approximately 1.6, which means that hydrogen fluoride is ionic, okay, because it's 1.9. So hydrogen fluoride is ionic. Then obviously you've got our regular salts, so like lithium fluoride, because lithium is, we can see it's 1 and fluorine's 4, same with lithium chlorides, it's 1 and 3. So then we can also look at lithium fluoride, or magnesium bromide. That's a difference of 1.6, which makes it ionic. Okay. Now, if we look at the middle, in the middle we've got obviously this region where it's quite a large region of a difference where it's greater than 0.4 but less than 1.6. So if it's greater than 0.4, less than 1.6, this makes it polar. So here we've got stuff like carbon and oxygen, which is about it's 3.5 for oxygen minus 2.5 for hydrogen, carbon, sorry, which equals 1. Or we've got nitrogen and hydrogen, which is 3 for nitrogen minus 2.1 for hydrogen, which equals 0.9. So all these molecules are polar, and if we just expand in on this whole polar thing, this basically means that there's a dipole in the bond. So this means that the molecule is partially negative and partially positive. So if we draw out a carbon to oxygen bond, we've got an electronegativity of 3.5 and 2.5, sorry, which means that the electrons will be on this side of the bond. Okay, and because this oxygen attracts the electrons greater than what the carbon can, this leaves the oxygen as slightly negative, whereas the carbon is slightly positive. Okay, so that's very important. This comes up in organic chemistry, where let's look at let's just look at propanone or acetone. So we've got CH3 with a double bond to an oxygen and CH3. So this oxygen is partially negative, and the hydrogen and the carbon, sorry, is partially positive, which means that this oxygen is now prone to attack by obviously electrophiles, which are attracted to electron-dense regions. I will get onto that more in future videos. So that's kind of a quick summary on electronegativity and how covalent and ionic bonds are the same thing. They're just two extremes of the same thing. So I hope that makes sense to everybody. I will be posting more videos regarding electronegativity. We'll be going into further concepts, understanding it more in future videos, and then I will also look at other important topics that I think will be very important for A-level chemistry. So I hope you guys enjoyed. Thank you for watching.